Hey, how are you doing? I'm good, thanks. Hey, fine.
think we should start. Good morning, everyone. Today, I want to discuss about the interpretation of Deepmarine process and the products. So now we are getting detail into one propositional environment, which is to the deep marine. I think most of you will have a question, why deep marine, isn't it? So the reason of why we have a deep marine interpretation in this course is because of the next slide. So the outline is this one for today. So in the beginning, I will give you a brief introduction about what is deep marine, and also the importance why we need to learn about this deep marine process and the products. And in the basic sedimentology course, you have this definition, I think. And also we will discuss about what kind of process that happens in the deep marine, and then what is the products for particular process. Next is about depositional elements in the deep marines. And the last two, this is our main topics. We try to interpret this deep marine by using qualitative and quantitative seismic interpretation method. So we will use we will use a seismic section, and then we try to interpret the qualitative part and quantitative part of the deep marine process and products. So the definition. Today there was, as I discussed in my seismic sequence stratigraphy. Today there is still a lot of disagreement about the terminology. Like you see here, we have at least two major definition about deep marine. This guy here, they define deep water or deep marine by quantitative number of the bathymetry, 200 meters. But it can be in the deep marine or in the lacustrine. Because in the lake, for instance, you also have, if you reach below 200 meters, so they call it as deep water. So they didn't define whether in the marine or terrestrial environment. So they just call it deep water, wherever you are, by 200 meters. And this is the guy, Samugan, Stowe, and Walker. And yeah, this guy, Samugan, he defined this deep water terminology. Especially, this is marine environment. So you see, this is land, and this is the age of the shelf, and this is below 200 meters. So from this point to the basin ward, they call it as deep water or deep marine. Another terminology is coming from this guy, Posamentier and this Pickering. They define the deep marine or deep water by physiography of the seafloor. So wherever you have the area of the shelf edge, this is okay. So if this is a bell-type system, you have a shelf in this area, and this is the edge of the shelf. So the area of the shelf edge to the basin floor. So this is the shelf edge, and this is the basin floor. Here, this is slope, and this is the basin floor. So wherever you have this configuration of the shelf edge to the basin floor, they call it as deep marine. Okay.
Do you understand lakes?
In the lakes, as long as you have a shelf edge, slope, basin floor, then it can be you can use this terminology as well. But normally they don't have they didn't use this in the lake. So this is actually passive continental passive merging case. And also it's the same with Emiliano Muti classification. You know about this guy, right? Emiliano Muti classification about turbidite system. So it's the same with Muti as well. So the importance, why we need to learn this Deepmarine process and the products. First of all, it's because of this one, the natural resources. This solid color is the Deepmarine province in the petroleum exploration and production. You see, it's almost everywhere. Even we are here in Trondheim, in the mid-Norwegian Sea, and in the whole Barents Sea, the most prolific petroleum province in the Deepmarine setting. So this is the first reason. It's because of natural resources. The second reason is because of this natural hazard. If you have slope like this, and you have slope failure, then you have this gliding movement or mass movement that can create this tsunami. So by looking at this feature, the Deepmarine feature, and then by monitoring this feature, then you can at least make a prediction when this tsunami can happen. Okay, process and products. As we discussed before about the sequence stratigraphy, we always dealing with the controls. What is the controls that cause this process and the products or this feature? So in the Deepmarine process, you have, I will draw the outline. So we have this point, self-H, this is slope, and this is basin floor fan. Okay, so we have this terrestrial and this guy here. And then this part from the self-H to the basin floor, from this one to this one. This is our focus area today. So, what is the controls to influence the sedimentary process and the products in this area? First of all, we have this guy here. This we have a source, a sedimentary source from the terrestrial area. So the difference between carbonate and plastic will give you different type of the process and product as well. So the first one is the sedimentary type, plastic, carbonate, what else? Biogenic, evaporate, volcanic plastic. The second one is sediment supply. So if you have meandering river, and then you have a delta there, river, yeah, and glaciers. We have it in Svalbard, for instance, for the glacier system. It also influences the process and products in this area because in the river, usually you have more erosion, right? But in the glaciation, you have more erosion and it's quite rapid because you have evaporation, you have erosion in this terrestrial, sent to this river and pump to this area. But in the glaciation, it's a periodic erosion. You feel like supply because it's periodic. Tectonics, yeah, if you have a subsidence in this part or you have uplift in this part, it can influence the process and product. Because, for instance, if you have uplift in this part, then the physiography of the seafloor, for instance, will be high. And you see, when sediments comes from this part to this part, mostly it's because of the gravity flow, right? But when you have high, so the sediments that comes from here will block with the high here. So the tectonic will influence the paleobathymetry or paleotopography of this seafloor. Okay. The last one is sea level. Yeah, we discussed a lot where you have a sea level rise, we have a sea level drop, what kind of stacking pattern that you have progradation, aggradation. And I think I have a figure of this. Yeah. So this is just a conclusion for this for controls on the process and products in the Deepmarine system. Have you seen Deepmarine rocks? Turbidite? If you haven't seen one of the turbidite rocks, this is one of the example from Ainsa, Southern Pyrenees. This is very fine sandstone. It's part of the, if you use multi classification, this is part of the low density turbidity current. If you use BOMA, this is a TC sequence. Yeah. If you just pass it, so you can touch the things that we will discuss here. So the process and the products. This is the whole. This is a summary of the process that happen in the Deepmarine system. So it's quite complete, mostly cover everything. This is the basic one. So if you see, this is the process that appear in the Deepmarine, and then this is how it looks like in the diagram, and this is the products. So what we want to do next in the qualitative and the quantitative interpretation is we want to relate this process and the characteristic using a seismic and then the deposits. So now I will give you some example about this guy here, because it's from here to here mostly similar. So how this process looks like. Yes, this will have. So this is an example of the mass movement that create a tsunami. Yeah, it's in the continental shelf. So this is a shelf, and this is self edge. This is slope, and this is a basin floor. Did you see that? I think if this one here. You see, This is the self edge, right? Sorry, this is the self edge at this sea floor. And then when the sediment comes to from terrestrial part or shelf to the basin floor, it will create the pressure on this edge. So then after that, when it's getting higher and higher, it will have this line here, and it collapses down. Boom. And you see this sea level is moving. Tsunami. And then it can travel 200 kilometers per hour. So, and then, yeah, this is when the tsunami hitting. So you have a sea level drop because of this movement. And when it comes back, then the tsunami is happening. Yeah, this is the okay. So this rockfall, creep, slide, slump is because of these things here. Mostly it's located in the slope. So you have a self edge, you have a slope failure, then you have this all this mass movement here. So the next one, this the turbidity current. I can show you here.
Apparatus. This first example is a turbidity current running down a ramp. You can see clearly the turbulent head, the body, and the tail behind. Seen from the other side, it looks very similar. Once again, you can see the turbulent head, the body behind it, and the very end of the tail. This is a front view with the turbidity current running toward you. This was taken with a GoPro. Here's a turbidity current running again down the same slope. Again, you can see the anatomy of the turbidity current. Once again, a turbidity current running down a ramp, but this time entering into an open basin, spreading out in a lobate shape, and encountering an obstacle, which it goes around almost over.
This lobate shape is one of the products of the Deepmarine system. And you see, if you see the grains in this video,
this is the same turbidity current.
Look at this
grain from the GoPro inside the actual tank.
The grain is mostly the same, right?
From one of the GoPros in the tank, but looking down on a turbidity current below. Lastly, here's a video of turbidity current of looking down from above.
So this lobate things is one of the Deepmarine products that we will discuss later. And also this terminal here is also one of the product of the Deepmarine system. Okay, if you remember the grain here, look at this grain. So it's mostly in the same grain, right? But if we compare to this debris flow here, you see you have a heterogeneous grain. You have a blocky, you have a gravel, you have a fine sand together. But in the turbidite, it's mostly the same, more or less the same grain. So this is the difference between this debris flow and this turbidity current. In the terrestrial environment, this debris flow also they call as a avalanche. If you have a snow avalanche or landslide in the fjord, just so rock fall coming boom, so that it's the debris flow. And I will upload this paper, this STOW 85. It's describe the definition for every process and products. So what we discuss here, I just give you the most important things like this landslide, this turbidity currents, debris flow, and then if you want to know more detail, I will give you this paper in the Blackboard. Okay, next is about this bottom current. So if you have, I don't have this example here. So if you have this basin floor here, it's mostly flat, right? And then if you have a slope and a basin floor going like this, and also this is the seawater, so you will dealing with the salinity, thermohaline things. So then you have current in the basin floor that goes like this, right? So that this one they call as bottom current, and the deposit called contourite. And pelagic or hemipelagic is mostly because this is a water column of the seawater of this water column, and then you have a plankton, benthos, or all organic material that live in this seawater. When they die, they will suspend it and then deposit it in this area. So this is what they call pelagic or hemipelagic. You see, you have this organism living in the sea, and then when it's die, then they are suspended to this basin floor. Okay, so this is the depositional elements that summarized by Possamentier and Walker, 2006. So mostly cover the whole depositional element in the Deepmarine system. So now we try to put all the sedimentary process in this depositional element. So in this staging area here, this is self-age. This is self-age, right? And then this is a self, and this is this age of the self. So you have canyon here, and then in this canyon mouth here, you have what we call as grain flow, and the fluid, all this guy here, grain flow, fluidized flow, liquid fat flow. So this flow mostly located in the proximal part of the canyon system. This one here. And as we discussed before, in the self-age here, if we have a slow failure, then usually we have a rock fall or slide or slump. So this process mostly located in this area here. And then in this canyon or channel, we have this debris flow. So this debris flow is mostly the material that comes from these cells. Or you can also have wall failure. So this is a canyon and this is channel. This is the wall, right? So sometimes you also have a wall failure that create sediment to this canyon and channel system. Next is about this contourite, or they call the sediment waves. So because of current in this basin floor, they create these sediment waves. So in the contourite, mostly located in the basin floor. You can have contourite in this slope here because you also have a current going like this. But the possibility to preserve this contourite in this slope is less, because imagine if you deposited contourite here, then after that you have a slump or scars, then everything is moving down. So most of the contourite are preserved in this area here, the basin floor. And then this is the breeze flow, and this is the turbidite. So where is the turbidite and this pelagic located? Abyssal plain here. Yes. Any idea? Turbidite. We saw the video before. It's like, and it's from the terminal to the lobate shape. So basically, turbidite is everywhere. And also the same as this pelagic. Wherever you have a sea level, then you always have a organic material, and when they die, then it's suspended to the seabed. So turbidite and pelagic is everywhere. Okay. Now this is the important part. So we try to interpret the depositional elements from the seismic. So if you get the seismic section, then how you interpret the depositional element from your seismic section. So we will use seismic stratigraphy approach, this one here. So we try to locate all these criteria in every depositional elements. So I need you to pay attention of this, because this is gonna be fun. So the first one, maybe we can start in the staging area. So in the staging area here, you have a canyon. Have you seen the Monterey? If you go to in the Google Maps or Google Earth, if you go to western part of California, you have San Andreas Fault. Then more to the west, you have Pacific Ocean. Then on the south edge of the California coast, you have a big canyon. They call this Monterey Canyon. It's modern canyon. So it's mostly a V-shaped feature in the basin floor, and it's wide and height. It's a big feature compared to channel. Yeah? No, we don't have. There is no criteria for that. But mostly the easiest thing to differentiate between a canyon and a channel. The canyon mostly located close to the self edge, but the channel is located more distal to the basin floor. So first is about the head of the canyon here. So then I just make number 1 here. So in this canyon, seismic reflection termination. So what kind of seismic reflection termination do you think you have in the proximal part of the canyon? So usually you will have something like this, and then all this strata below is truncated by this erosional surface of the canyon, right? I'm sorry? Oh yeah, it will like later. I will discuss later. And then this is seismic reflection termination and seismic reflection configuration. I can put this one. So what kind of configuration do you have in this upper part of the canyon? So any idea of the reflection configuration? I'm sorry? Oh, you mean inside? No, I mean for the canyon fill, it can be anything. It depends on the sedimentary source. If you have a source from the river, for instance, and then deposited there, then you can have a grain. But if you have a pelagic mud, so it's just low amplitude, for instance. But for the reflection configuration, mostly, what do you think? Oblique. This is only small part of the big system. So so most of the configuration is something like this. So it's a V shape with erosional truncation below. That's the configuration. So configuration is a V shape with truncation. Continuity. So mostly this surface is continuous because this is in the this represent the seabed, right? At the time. So this surface, the canyon surface, mostly continuous. So number 3 is continuous, except you have a fault, then it's not continuous. But normally this is continuous because this is represent the seabed. Amplitude. Oh yeah, this is the I think lecture number 3 about seismic facies analysis. So we try to implement the seismic facies analysis in this lecture. So amplitude, what kind of amplitude do you have? What is the definition of the amplitude? In this surface here, normally you will have a quite strong amplitude because it's a cut. The surface is cutting everything here, and it's mixture between the below the formation below. So it mixture everything. Yeah. Sorry. This one? It can be anything. I will show you a sample of the canyon fill that contain low amplitude because of the mud, pelagic mud, and with the middle amplitude of layering of a fine grain. So the canyon fill can be anything. So the amplitude, usually we have quite strong amplitude in the surface. frequency. I think in the Kama lecture, it mentioned that if you have layer like this, it means it's a high frequency. If you have layer like this, it means low frequency, isn't it? Yeah. So in this canyon feature, if you have the canyon fill with a lot of drain, so this is a high frequency. But if the canyon filled by pelagic mud, then it's low frequency. So in this canyon system, you can have both low and high frequency. Number 6, interval velocity. So it can be, it's possible to have both low and high velocity, depends on this canyon field. So both external forms. So what do you think for this external form? Slope from view? No, I mean this. So basically, the external form for this is something like this. Yeah, this is the external form. So you have this V shape, and then with this canyon wall. Okay. Okay. Oh, so now it's done. Next, maybe we can go to channel because it will relate it. So we have this canyon here. This is A. This is A. So from this canyon down here, we have a channel. Okay. So now this is B. So this is B. Seismic reflection termination. So in this channel system, usually you have similar with the canyon, but with more major physiography. When I said major, means it's because of you have more erosion compared to the channel, compared to the canyon. Because remember, this is a slope, this high slope. Then everything just move directly to the basin floor, right? Or to the canyon. So that's why in the canyon you have more erosion than in the channel you have more erosion compared to the canyon, because you see when you have V shape, it means that the erosion is less compared to the U shape. So the V shape, and the U shape. So in the channel, The difference is just the shape, but everything is truncated like this. And this is also represent seabed at that time. Okay. Seismic reflection configuration is the same. We can say U shape with truncation. Continuous, yeah, it's continuous. This surface is continuous. Otherwise, you don't have a channel deposit. And amplitude, it's the same. You can have a strong amplitude in the surface. Strong amplitude in the surface. But for this channel fill, it can be both. It depends on what kind of sediment type that fill the canyon. Frequency is the same. You can have low and high. Velocity is the same. You can have both. And external forms is something like this. Did you see the difference between the form here and here? The shape, yeah, this is U and this is V. And then look at here, I make it very sharp to the proximal part, but here it's the same. So that's also the difference in the canyon. In the canyon, because then this is related to the self-edge, so it's become narrow, but in the channel system, more or less the same. But what do you call it in the seismic classes? This form? This is just the terminology, but if you draw like this is the same. Just the name of this. They call trough fill or channel fill. Yeah, it's the same. So next, canyon, channel. Then we go down to, maybe you can try the basin floor fan. Or Levy channel, maybe, Levy channel. So, remember in the slope setting, you have a different angle, yeah? So you have a relative flat here, and then you have a high angle here. Then you have a relative low here. Then this is the flat one of the basin floor fan. So when the channels enter relatively low angle, then you will have what you call this meandering channel. Yeah. So you have this meandering channel here, like this. When you have this meandering channel, if I make a cross section like this, maybe from a small to B small, can put it here. So from A small to B small, you have something. This is A, this is B. And the current direction is outward the gridboard, yeah? So if you look at this physiography, you have the channel here, and you have this what you call this natural bank, okay? And then this natural bank, when the sediment is filling this, and then if you have if this channel cannot accommodate sediment, then it will going like this. Okay, that's what we call as channel levee channels. So when you sediment, so if you have a sediment more than this volume, then it will appear to the other side. That's what we call as a levee channel. And in this levee channel, what we have, this is C. So C, something like this. So this is the reflection termination. So you have something like this, like a sheet. But you see this sheet with mounted, right? Reflection configuration. This one is sheets with mounted. Yeah. The edge of the channel field. Yeah. Oh yeah, this is connected to channel flow. But then when the material is the volume of material is bigger than this volume of this U things, then it will deposit it to the other side. But this is on the channel flow. Do you want to have a break? So we have 10 minutes or 15? 15? So we met 9:20.
Hey, morning, how are you? Yeah, I'm good.
I wanted to know when we speak about
external form in the canyon. You said that it's like V-shaped structure, but there is no example of it. As I know, we have slope fronting.
Yeah, yeah.
But it's not the same.
No, this is for the slump. Slump.
Yeah.
No, they don't have. They don't have for the canyon. But because when they say external forms, it means that you just make a three-dimension of the picture. Then you don't need to name it. Just this is the external form because I think that I don't find any external form
I
for
also
this.
do.
Yeah,
So
no.
even for
For the channel.
LED as well,
No.
and channel as well. So this what you're explaining right now is deep sea current channel, unlike deep sea channel.
DP channel. DP channel. It's a
It just look like meanderings. That's why you mentioned.
yes, because it's more or less flat. I mean the slope is already flat.
And here when we have the in 3D canyon, can we also as a reference point see the shelf age?
You should
Because this and this difference only D and
yeah.
U, right?
And the
But-
position. This one is upper slope.
Yeah, but we don't know it when we're just seeing 3D view
Oh, yeah,
and we don't know anything else. Here U, here V, but here also we can see probably H shelf.
Yes, you should
If
have.
you will, if we will interpret it right.
Yeah, normally this point is the self-edge point.
Yeah, and about type of the climate zones, for example, probably Petroleum explains that we have a delta here zone, we have shoreline break here.
Yeah.
So it's probably sigmoidal type of climate from here, and we're going to the deep sea here. We will get a oblique climate because if we will go we have kind of climate.
Yes.
It's oblique.
That's obvious. But I didn't focus on this platform because if you see, this is only one stratigraphic timelines. So in one stratigraphic timelines, you have a different depositional elements. So I didn't discuss this platform because then.
Just wondering.
Yeah. In one, so for instance, you have one planoform. In the one planoform, this is planoform surface.
Yeah, it's marginal.
Yes, marginal. So
But I'm talking about that particular.
oh yeah. You can also have another depositional element in the previous planoform.
And you didn't speak, or I missed about the source of the sediments. Like we can have a hemipelagic map, but what
Yeah.
about sun?
Yeah, we in the second slide.
Insect.
The second one.
I'm just wondering, so like the basic foods, it's formed, right? Like
Yeah.
there's no difference in sediments.
No, it's the same. It depends on the sediment type of the source. But mostly in the beginning of the process, they need to erode it.
Yeah.
Yeah. So when you need to erode it, then you need to have a coarse grain. But later, when you have eroded, then you have a bowl, and then the filling is can be anything.
This is really,
This one, this is the levy.
yeah, so like what is this?
This is this is a current directions. So it means I want to show this is a section, and the current direction is going outward.
And this is like stuff.
It depends. It depends on the source in here.
But why we get into this levy? Because of curvaceous of the channel?
No, because of when the sediment come from behind the port, so this one, and then the flow carry a lot of material, right? So when the amount of material is higher than this volume, then it will go to this
So
side.
it's not always like that. We can still get just U-shape.
Oh yeah. If the material is if this P shape can accommodate a volume of material that they carry, then it will go through the submarine vent. But if the material is higher,
Okay. And can you go please to the previous slide? You said something about the risk flow.
Yeah.
You remember? Yeah, you said that for 3D guides, main sources with risk flow, like a type of accumulation. But what about slumps?
no, the turbidite, it can be anything. So the debris flow can translate into turbidite further. the more distal.
Yeah, but why not slump?
Islam also in Islam
It's similar.
it's the same. So first you have a slump, but if you go further to the distal part, then it can be turbidite or the breeze. But this one is the initiation initiation of the process.
But in seismic slump and the breeze flow look the same, right?
In the slump and the breeze flow, slightly different. In the slump,
We have chaotic rounded appearance.
you have a chaotic, but you can in slump sometimes you can trace the layer. I have
In slump.
in slump.
Okay.
I have an example here. This is the slump. So you can trace this layer, and this is the chaotic things inside. But then you still can trace this layer here. So that's slump.
And can you please, when you will give explanation for next pages, also mention energy, the positional energy, because as it's mentioned, we have this, but we also have an energy. That's the next point.
Oh, the energy will relate to all this stuff. So after we define this, then we can say this is high energy, low energy. Because the energy needs to refer to all this stuff first.
Yeah, it's referred to all this stuff, but sometimes it's still difficult to know, even you know all this stuff. It's, for example, for me it will be difficult to say for channel, this meandering type of the channel, deep sea channel, have a low energy or high energy.
Oh, then
even you will mention all these parameters, but still it's difficult.
Yeah, for the energy you need to look at all this stuff and then summarize what kind of energy.
It's not like it's written in the book.
No. You need to look at all this stuff and then make a summary of the energy. There is no template that
Because in articles usually they say okay, for this kind of external form we have this energy for this.
But if you look at another chapter, they said if you have strong amplitude or low amplitude, it means you have a fine material. It means low energy. So when you say energy, then you need to look at everything.
Can I just quickly look at the previous slides that I missed? Just to see what you showed.
I show this one,
Yeah, okay.
this one. So we have two different terminology. You can read this.
Yeah.
And then the importance why we need to learn Deepmarine because of this. And then this is the controls.
Yeah.
And then
This one.
You are here.
What?
You are starting
On
from
the
here.
next one.
Oh.
I've read through it.
So this is just process that happen in this deep water, deep marine. But for every definition, I didn't go through every definition. I will upload this paper. It's stated here. So it's the same here.
We had a lot of things.
Yeah, sure. But for, I think your geophysics, petroleum geophysics, or
Yeah, but then.
you have a segment already.
Yeah, like I'm taking this 5-year program.
Oh, you have it. Okay,
Yeah,
that's
we had-
good. Okay, that's good.
But what is?
This
Did you send it to?
Yeah, I sent to the student because this is an example of turbidite deposits, and this is from INISA.
It's really hard to support the part.
Yeah, this is fine, very fine.
Okay, so it's not that like.
No, it's only a small part of the of fine grain.
Because like turbines are usually like half a meter like sequence.
Oh, it depends.
It can differ.
It depends on amount of sediment supply.
But what, like from what to what?
No, there is no agreement on that. It can be 14, like the one that I showed the video. It's centimeter scale, but it can be up to meter or kilometer
Yeah,
scale.
in England it seems like they were about it.
Exactly, in Dorset.
What?
Dorset or Devon. In England, in Devon or the place. Yeah, it can be between centimeter to kilometer scale.
Is there any?
Yeah, power.
Is it okay?
Yeah.
Dicky, when you said pelagic,
Mm.
is it only organic pelagic?
Almost organic actually.
Could be just like mud dust or
Yeah.
mud particles.
Yeah, you can, but the mud particle will deposit it first compared to the pelagic mud, because in the pelagic mud is the organic still alive and still walking on the marine.
What is the difference between pelagic and hemipelagic?
It's the amount. So the hemipelagic is more moisture or more what do you call it? If you call saturation water, more saturated. Uh, Okay, can we continue? So we stop in this Levy channel. So the third seismic stratigraphy approach is continuity. So this part here that we discuss as Levy channel is also continuous. And for the amplitude, so in this type of system, this Levy channel, if you have a coarse or finer in this channel field, and then when it is overlap to the other side, then usually you will have interbedded between fine, coarse, and fine and coarse. But it's not always like that. So it depends. It really depends on what kind of sediment types in this channel system. So we can say in this amplitude, we can say both low and high amplitude. Frequency, mostly in this levy, as I said, you have interbedded between two different phases. So mostly in this part, you have high frequency. Interval velocity, it can be both. And the external form is the idea of the external form is that you make a 3-dimension of your feature. That's if you don't know what's the name of this external form, because it's a lot of name here, but if you don't know the name, just create a 3-dimension of the feature. Yeah. You can have a low velocity and high velocity. You need to have a well, yes. Yes. All indication. So for this external form, can you see this part here? You see, we have this levy in the 3-dimension, hopefully. So this is the external form of the levy. You have a sheet with the mounted close to the natural levy. Yeah. No, when I say low and high, it's for the whole deposits. For the surface, it depends on, as I said before, you have interbedded between fine. Oh, here. No, this one is the channel. This is a levy. We talk about levy. Not. So we didn't discuss about this. So we discuss. This one is here. But why I draw the channel? Because natural levy always related to the channel. So that's why I need to draw the channel. But we discuss the channel here, okay? So in the natural levee, you see we have interbedded between between two fascias, and then the shape is you have a sheets like this, and with a mounted close to the natural levee. This is natural levee. So this one is natural levee.
You will get layers of fine sediment and layers of cocoa.
It depends on the source of the sediment, but I could say you will have two fascias.
And the one you have to do the other one.
Yes. Okay, next, I think we should go to the submarine fan. Yeah. Oh, yeah, because of sheets, and then it's interbedded between two phases, so mostly high frequency.
But it's possible area for reservoir or if it's sandstone.
It's possible for reservoir, but then you have a challenge with the vertical permeability, because in this channel phases, the vertical permeability is good because the different phases is just you have pores fine, but it's connected. But in here, you see this layer, this sheet, that's the boundary for the permeability. So you have a challenge in this devotional elements for the reservoir. And then if we go further down, we will have this submarine fan. Yeah, it's at this one frontal split is the submarine fan, and also this one. So in this submarine fan, what we have is reflection termination. So if I make a cross section from here to here, C to D, what you have is something like this. So this is C to D. Okay? From
Submarine fan or deep sea fan or turbidite actually sediment do the same.
turbidite is a process. Submarine fan, deep sea fan is products. So you need to differentiate.
But when you have a turbidite and down
Yeah? Yes. C to D, like that. So this is the shape of this section. And then the reflection termination, usually you will have something like this. But then you can have something like this, right? The what? This one here. But then in this picture, you have a channel coming in like this. This one? No, because this is to be, maybe you can say this one here is a one fan, this is another fan, But you see this dot lines, this is another channel. So you have a fan somewhere here for this channel. For this channel, you have fan somewhere here. So this is still a channel. But you can say like this one. This is 1, 2, 3, 4, 5. Then you can say this is one fan. This is another one fan. Like that. So this is reflection termination, yeah. And then reflection configuration, you can say mounted shape. Or what mounted, or they call also fan. And the number 3 is continuity. So continuity of this surface here is usually continuous, but inside here, then sometimes it's not continuous. Because remember the turbidity current, then inside, when the turbidity current stops, then you have this layer here deposited, and then this is continuous, but inside is not continuous. So we can say surface is continuous, but internal deposit or internal character, we can say not continuous to moderate. Number 4, 1, 2, 3, amplitude. Any idea? What kind of amplitude do you have? And also in this submarine fan, normally the grain is much more finer than the channel, because this is more distal part of this is more distal, so the grain is much more finer compared to the channel. So we can say in the amplitude, we can say this one is low to high amplitude, because and for the frequency, what do you think for the frequency? It means the frequency for this internal strata, huh? Lower or too moderate. We can say low to moderate. Sometimes you have a layering, but sometimes it's just a chaotic. Yeah, this is low. If it is chaotic, it's low. So that's why I say low to moderate.
Yeah, but if you have a distinct, huge sandstorm flow and fine grain on top of the usually getting in somebody one, then it should be high pressure.
But it depends on layering. If you have a blocky of coarse and fine, so this is 2 layers, only 2 layers. So it depends on the layering. We say when we say frequency, it's about layering or interface, not the grain size. Okay, number 6 is what? Velocity. So, what do you think about the interval velocity? Any any idea? So as I said before, we have quite low to high amplitude here, and also it much more finer than this channel system. So what do you think? Any idea? Yep. So what is causing the velocity? Yeah. Yeah. You want to say something? Yes, yes. So it's also depends on the sediment types. So then what we can say from low to high. External form is going like this. So you have a mounted here, and when it comes to the proximal part, it's become narrow. Okay. Yep. So canyon channel ravine submarine fan. Next, maybe we can discuss about this mass transport complex. It's a slum slide. It's characterized by this mass transport complex. So if we have this self-H, then you have this slow failure, then you have this mass transport complex. So maybe we can take the slum. So for E is slum. So in the slum, as you see on the figure, you have something like this. Yep. So then you have so this is the self-H, and this is the slope. So you have this slum deposit like this, And then usually in the slum you will have something like this. And then the internal configuration will be, you have this chaotic below, and in the upper part sometimes you can see a layer. So number 2, the shape. What is this shape? This called yeah, they call slump. So the reflection, just reflection configuration, they call this as a slump. Yeah. For the continuity, what in the upper surface here is mostly continuous, but in the internal part is discontinuous. So surface, oh sorry, top surface is continuous. Internal configuration is not continuous. Amplitude. So, as the speaker said, that you have more chaotic feature below, and then you have some layering above. So, what do you think of this amplitude can be in this slump? So, this kind of a mixture between the chaotic and this layering things. And also it can the chaotic things, it can be blocky, or it's a big boulder, something like that. So for this lower part, maybe you can have a quite high amplitude, but then in the upper part here, maybe it's more really low amplitude. So number 4, we can say this is from low to high amplitude. For the frequency, I could say this is low because this layer above sometimes it's not continuous, so it's just like a local layer in this slump. So we can say this is low frequency. And for the interval velocity, we have this chaotic things. It's like a boulder or a big glass with this layering. So what kind of interval velocity do you think? Yeah, in this part you can have a low velocity, for instance, but then you can have a high velocity below here. So we can say this is low to high velocity. External forms is slump, but then we can say this. So most normally this is the self edge here. Then you have this slope. Then this is the slant things. Okay. I think that's the most important depositional elements in this Deepmarine system. Sorry? Oh, because you have branch of your channel. This point here is the point where your channel is branching. Yeah, this is of the channel. You see? This is the channel, so this is the point of. Yes. 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 This one is it look like a fan, but fan close to the not in the mouth of the channel, but in the side of the channel. So yes, yes. So I think we can go to the next slide. Yeah. Yeah. This you see, the gully is the same as a channel, but with the low sediment supply. So that's why I put it here, because if you see, there is a lot of sediment supply from this. So if I put here, there is no gully here. So gully, that's why I put it here, is the same as a channel, but with low sediment supply. And then normally, when you have gully, you don't have a sediment from river or delta, but it's because of a longshore drift current along this self edge. So that's why you have the gully usually is tiny, and it's you have several gully with the same geometry. Impacted by tide? Not really, because it's a subaqueous, but the sediments come from a longshore drift parallel to this shoreline. Yeah. Okay, I think we need to go to the next slide. So this also answer your question. So this is qualitative interpretation of the positional elements, and for the quantitatively, what we use is to use morphometry analysis. So we measure the width. I can show it here. So for the morphometry analysis, we use so if this is the feature of the positional element. So what we need to do is we need to measure this top width. We need to measure this base width. We need to measure this height. And the last one is the volume of this feature. So we could say this volume of cross-sectional area. So by measuring all these parameters, then we make a cross plot from this parameter to the distance along the slope. Then we can discuss about this deposition element and the sedimentary process. So in here, give you an example of crossplot between depth and width. From this crossplot, you can differentiate, right? Where is the canyon, where is the gullies, and where is the channel. So if you look at it, for instance, in the canyon, crossplot between depth and dips mostly located here, and gully is here. And this channel, either this or this, is somewhere here. So from this crossplot, it also can tell you about the depositional elements. Next is about qualitative interpretation of sedimentary process. So I have this surface of the erosional, and then we have a canyon, 1, 2, 3, 4, 5. We have slight scars, and also we have gullies here. So this is section 1, 2, 3 is 1, 2, 3. So this is proximal, and this is distal of this canyon system. So if you look at this, this is the red dashed line is the canyon surface, and then you see it's faulted, so it's not continuous because of faulted. And from this feature, we can see that the way that you need to you see this canyon surface is located in this black reflector, right? In this part is showing high amplitude. This one is low amplitude. This is high amplitude. So it's a mixture between high and low amplitude because, as I said before, when it's eroded, then it's mixture between the formation below and this material that brings to eroded. So in this location here, what you have usually, you will have this wall failure of the canyon because this is more proximal. So you have a source from here. You have a canyon failure here. This is an example of the canyon mass movement or failure things. And then you also have debris slope. You also have this pelagic mud. Did you see this white high amplitude? This is, it means that high amplitude reflection element. So this white high amplitude is a product of this rockfall or debris slope from the canyon wall. Because you see, it's very localized at the base of the canyon. So this is a product of this mass movement in the canyon, in the proximal canyon. And then next, if you look at this medial canyon, you see this canyon field is filled by two facies: massive low amplitude reflection element, this guy here, and continuous reflector element, these things here. So in this massive low amplitude reflection element, mostly is because of this pelagic mud. But when you say this, this pelagic mud is this one conformable reflection element, but this massive low amplitude is because of a fine grain sediment from the canyon flow. Why I said that before? Because if you have this, you see this conformable reflection element, it's like topping your canyon after everything is filled, right? This bandit is because of a differential compaction, because this one is lower than this one. So normally you should have something flat like this. So this flat here and continuous is because of this pelagic mud. Remember when you are in this area, you have everything is the animals, the plankton benthos is living here, and then when they die, and they just covering everything, the whole things. So this is the products, and this also we can use as a marker. or reference surface. It depends on the contrast. It depends on the contrast. Yeah. This one? This one is fine grained sediment, like it's a sandstone. But this one is a shell or mud, you can say, because of this pelagic things organism. But this one is plastic. And then you see now more to the distal, we still have these conformable reflection elements, but with this phases here. So we can have this the breeze flow, turbidite, and this pelagic mud. Okay, next is about the quantitative. Before is process qualitatively, and now is quantitatively. How we know the sedimentary process by make a quantification of it. So we use this method, the morphometric analysis, to quantify the sedimentary process. So we make all the cross section. We have in this surface we have this C is canyon, so we have 5 canyon. We have 2 slide scar and we have 4 gullies. So we make a cross section every 200 meters from every canyon. So it's a lot of measurement. And then we make a cross section on this every section here. So this is how the physiography of canyons looks like from the proximal to the distal. From the proximal to the distal. So from the shape, you can also say something, right? Like for instance here, in the canyon 1, the shape, the V shape is narrow, but when it goes to the proximal, it's wider. It means that the erosional surface, it means the erosional is higher in this part and is lower in this part. Because of only because of the V-shaped canyon. This is narrow, and when it comes to the distal, is wider. More erosion. Yeah.
But the narrow one is typically deeper.
The narrow one is typical, not really. And then we make a cross plot for every morphometry analysis. Make a cross plot with the canyon distance. Sorry, with the sediment conduit distance. So for instance, from here to here, then we make every 200 meters, and then this every 200 meters is also represent this morphometry. So for instance, this is a plot between distance with the depth from the canyon, all the canyon. I put it in one system, and also this degree is a slope gradient. You see here when it the depth, this one goes to the distal part, and this is proximal. So when going to the distal part, the depth is higher, and also the slope gradient is lower. Yeah.
When it's become wider, why not we also to the channel?
Actually this one is different because we don't have channel here. So this is only a canyon system. What?
Just from the seismic, how can we know
Of
from the seismic sequence that we report?
yes.
How can we know if it's, like, for example, here in canyon or
Oh yeah,
channel?
I get your point. In this canyon, it's wider, but it's still V-shaped. Look like this. This is wider compared to this one, but still V-shaped. But in the canyon, sorry, in the channel, exactly, it's mostly U-shaped.
So it's really easy to see the
Is is quite easy, especially if your section is large. So for instance, you have a section, regional 2D section, from shelf to basin floor, then it's easy to plot the canyon, usually close to the shelf edge, and with the slope, with the high angle of slope, but canyon mostly located close to the basin floor with low angle of slope. Sorry, channel slope, yeah, sorry. So canyon is more upper slope, channel is mostly down slope. And also look at the physiography, the P and the U things.
Maybe after.
Yeah.
Maybe just, do you have after that maybe an analysis just of the other channel maybe?
Yeah, I have it.
Okay.
I have it. The reason why I explain like this because I want you guys to know the basic understanding about the things. I mean, for if after this, then it's easy for you to look. Okay, this is channel, this is loop. Because if I just give you, this is also a seismic section example from real data. I mean, if I give you all this stuff in the seismic section, then I think you don't need to come to the class.
But after making more primitive analysis of the canyon and it did result what the trend is okay.
Oh yeah, after the cross plot, yeah. So sometimes the trend is not okay, like this things. So this is height, these things, compared to the depth. So compared to the distance. So if you look at here, usually if you have canyon, yeah, from proximal to the distal, height will be higher to the slope to the down distance to the distal part. Like here, this is proximal and this is distal. The height is higher in the distal part. Because if it is proximal, then it's smaller, okay? Did you agree? Huh? So if you look at here, in this proximal part, all the height is smaller compared to the distal part. But you said the trend is not really good, not always good, because look at this green one here. You see, you have a jumping here and boom, like this.
Why it's like that? Because measurements is not correct or because of something?
Measurement is correct. I have uncertainty in the depth conversion for sure, because when I measure the height, I need to convert my seismic into depth into meters. So the uncertainty is like 5 to 10 meters, but it's not really appear here. The problem with this is that in this part I have a fault. So there is a fault in this area here. 250 meters. It depends on the length of the canyon. You can make it as smaller, but then I need my Petra will will busy. But you can make it detailed for sure. And also look at this thing here. This canyon here, canyon number 5, from proximal to medial is good, but when it goes to the distal part, boom. You see, wider, height, higher, and then smaller. This is also because of the fault. So I have a fault here that uplift the part of the canyon. That the fault is after canyon deposition, okay? Not before. Yeah. Sorry. Oh, you mean the depth from here? This is the depth from a seabed to here, to the base of the canyon. Regional surface. Oh yeah, actually this canyon is close to the seafloor, so the compaction factor is not really happen.
What's the distance between the canyon?
The distance between the canyon is small. It's like less than 10 kilometers. Okay, I think this is for the slide scars. So it's the same. You see, we have a narrow here and wider to the distal part. It's the same as this one as well. But the difference with this slide scar is that it's the depression is caused by a slope failure. So that's why the shape is not V or it's not U, but it's wider. It's just wide. And this is the plot. You see, everything is smooth, linear, like this. So in this case, we can say that. So for instance, the height here from the slide scar 1 and slide scar 2 has a linear trend from proximal to distal. It means that when the slope failure is down, so everything is just moving. And then let's see. And is there any question about this slide scar? The canyon is quite complicated because it's faulted, so that's why you see from look at this width, it's up and down like this. But the trend is the trend for this width, for instance, everything is increasing to the distal part. But in the middle part, you have a up and down because of the fault in this case. It's the same with this one. Oh yeah, and then also I want to mention about this. This is another important thing. So this is gully. So if you look at my surface below, this one. So I have a source of sediment from these directions, and this is the self edge, going like that. But this gully here, they don't have any source of the sediment. So this gully is just because of longshore drift current from this to this directions. So the process of erosion in the gully is less than canyon. And then if you look at this, we have a gully 1, gully 2, gully 3, and gully 4 here. I want to mention, and also look at this morphometry here. It's tiny channel, like a channel, but it's very tiny. And also this point here, you see this they call it as knick point when it's moving like this. It's also representing this point here. So this is gully number 3 here. Gully number 3. This is gully 3. So this point here is represent the knick point. This one here. So it's appear in this cross plot as well. But the trend is the same. It's the increasing in the number, in width, in the height, but the amount is smaller than channel and the canyon. And this is the reference that I use for this course, mostly the basic one. And this is example of the slump in the outcrop. So imagine if I withdraw the one before here. In the slump, you have this, in the upper part, you have this layer here. That's a banded. And in the middle, it's a chaotic. And below is even worse. So this is the example of a slump from the outcrop. Any question? I think I used 10 minutes. Thank you. Lecture is over. So now it's exercise. So you're working in the project, and then you have, I think you have 1 month or less, or more or less.
Yeah, 7 to 8 months.
Yeah. Then so I think you should.
You have to submit saying that it's 13th.
13, yeah, you have to submit the poster on the 13th of April. No, 17 is the presentation of the poster, but you need to submit the poster. I think I put on the blackboard the date.
Can you announce about the reference group if they want to something?
Oh yeah, and also if you want to say something about this course to the reference group, you can just ask you or Guillaume. Yeah. For the poster, yeah. I think I put it in the black. Have you seen on the blackboard?
Just I wondered to ask
About the date?
because I know one of the last record video, but
Yeah.
it wasn't clear.
Yeah.
No.
I asked actually the guys who made the video and they told me it's gonna be like
But the date
animation
of
video
the submission of the
website
poster.
of the Petroleum Institute.
You already uploaded, you will upload.
They will upload.
But what about next lectures? Because as soon as you will
This one,
decide,
come here.
we will miss all lectures.
So,
That's why.
course
So it's
4,
better if they allowed us to
Project.
record it. It's better to do it as soon as possible, to not miss results.
Update.
We have recorded. We have recorded the video.
This one as well.
No, it was only in the
Only one
submission,
lecture.
only one.
But
Yeah.
what about next
No,
one?
no, it was only one.
It's impossible to record
Okay.
next one.
No, no.
Why?
Yeah.
I think so. I can.
Yeah, I just wondered.
Yes, I will.
I was just wondering about the group, but I don't know, you probably were. You
What?
were first.
No, it's course and fire. I have a meeting with this reference group after this. So if you we can discuss after I have a meeting with this guy. Okay. Hey. Hey.
Meeting at Hugen or what?
Yeah, I just used the lecture lately. I think you take it here. Is there any guy up there or Kamal also? No?